modern healthcare AI is increasingly discussed in research, in the media, in politics, at the dinner tables. The idea that a machine or an artificial intelligence should make crucial decisions about my healthcare or the healthcare of someone I love is daunting, but knowing that this artificial intelligence can be just as biased, as racist, or as sexist as the worst of men is terrifying. So if we want to be able to get the best out of AI for healthcare, we are forced to find ways to minimize the bias and get transparent, safe AI solutions. So let's take a look at where this bias might come from. We'll start with a toy illustration based on a very real case. You should imagine using predicted depression risk scores for prioritizing resources, such as referral to a psychologist. Now, in Denmark, there are similar cases used in real life to prioritize other healthcare resources, so this is a rather realistic case. Now, we know that depression is diagnosed more commonly in women than in men, and we know that this is partially due to different cultural perceptions of gender and of depression. We also know that if we slightly change the diagnostic criteria, including aggressive symptoms as well, then we start diagnosing more men. So there is good evidence that men are actually underdiagnosed with depression as it is. If you use these diagnoses to train a machine learning algorithm, then the corresponding algorithm will also be skewed. It will be unfair. So let's simulate how this happens. Now, you should imagine a disease model where disease is scored from 0 being healthy to 10 being severe. This is the true disease score is what you see along the x-axis in the plot. And a true diagnosis corresponds to a threshold of 5, meaning the people on the right-hand side are ill and those on the left-hand side are healthy. We have two groups of people, red people and blue people, where the blue people are systematically underdiagnosed. We model this by multiplying their predicted disease scores by a factor less than 1. And we also assume the diagnostic criteria are more appropriate for the red group than for the blue, and we model this by having a higher noise on the blue people than on the red. Now, if I apply the diagnostic threshold of 5 to my diagnosed or my predicted diagnostic scores, you see the true positives are in the top right corner, and for the red group, they're perfect. The true negatives are in the bottom left corner, and for the red group, again, they're perfect. Whereas for the blue people, you have a significant amount of people who are not diagnosed, although they are ill. This is what you see in the bottom right hand. Now, you might say, maybe if I adjust my threshold a bit, I can do better, at least for the blue people. So let's take a look at what happens if I start out with a threshold at 0 and slowly move it up. Now, if I do that, you see here in the plot, for the red group, with the red curve, the diagnostic accuracy gets better and better and better, and smack in the middle, you have the perfect predictive accuracy that we saw on the slide before. The blue group never reaches perfect prediction. It reaches a peak at about 80% diagnostic accuracy. Now, some notions of fair algorithm ask that you get the same predictive performance for two different groups. Here, the red group and the blue group. So if I am to get the same predictive performance for the red group as I now have for the blue, there are two ways I could do this with two different thresholds. Let's take a look at what those thresholds do. Now, this is the optimum threshold for the blue group, and you can see quite a few of them are actually diagnosed correctly, but I also make two types of mistakes, both false positives, where I diagnose someone as ill even if they're not, and false negatives, where someone is not getting a diagnosis even if they're ill. For the red people, I only make one type of mistake. Now here I have false positives, meaning that there are healthy people that are diagnosed as ill. And for some diseases, this can actually be problematic, because for some diseases, the treatment is also harmful. So if you get harmful treatment for a disease you don't have, that's worse than not being treated. Now, in the other threshold for the red people that gives the same performance as for the blue, I now only have false negatives. And again, here I am not diagnosing people who are ill, which is obviously a problem. So while I have sacrificed my performance in the red group by saying I want to be just as good at diagnosing red people as the blue, I still have a bias in the types of errors that I make. And depending on how harmful those errors are, that can be a problem. Next, we look at a real case. where we look at computer-assisted diagnosis, where a neural network is used to diagnose thoracic diseases from X-ray images. This is a paper that came out in the spring, and here the authors use a very large data set that allows them to curate smaller training sets where they start out training only on men, so they are training the algorithm to diagnose men, and then they start replacing some of those men by women, so they have 25% women, 50, 75%, and at the end they are training it only to diagnose women. And what you see on the left-hand plot is how these algorithms perform when it comes to diagnosing women. And you can see when it's trained to diagnose men, it doesn't do all that well. When you add more females into the training set, you get better and better performance. What you see on the right-hand side is what happens when you test the same algorithms on male patients. And here, the best algorithm is the one that's trained on men, and as you move towards training on more and more women and fewer men, it gets worse. This is not so surprising. What is surprising is what you see if you look at the y-axis, because the best algorithm for the women, it has about 75% diagnostic accuracy. This is the one that's specifically trained to diagnose women. That same algorithm performs at 5% points better at 80% for the men. So already here, this algorithm that's specifically trained to diagnose women, it's better at diagnosing men. And when you start adding men into the training set, these two thresholds move apart. As a woman, I find that very unfair. As a machine learner who might be trying to diagnose or construct fair algorithms, I also find this very frustrating. No matter what I do, I'm bound to get a discriminatory algorithm. So summarizing this, where does bias in machine learning come from? Well, it can come from discrimination being embedded in your training data. If you're training your algorithm to imitate people who are biased, well, the algorithm will be biased as well. As we've just seen, it can also come from imbalanced training sets. And both of these two things you can do something about. You can tell your people to stop being biased when they are acting as training sets, or you can try to curate your training data to get equal representation of groups that you care about. But you can also get bias from other sources. For instance, if you have different levels of label noise or diagnostic errors in the two groups, if it's harder to diagnose men than women, you have different training conditions for those different groups. Similarly, if you have different feature distributions for the two groups, for instance, if the disease patterns are different in women than in men, then again you have different training conditions, meaning it's simply more difficult to create a good algorithm for one group than another. Now, if you add to this that historically the entire medical knowledge base is largely based on the white male anatomy, well, you're bound to have bias in your algorithms. So what can we take from this? Algorithms are new and biased algorithms are scary, but bias is not new. It's already there. And on the more hopeful side, algorithms come with potential for early discovery and mitigation of this bias. So in order to try to mitigate this bias, let's try to define what it is. Because over or underrepresentation of certain groups is not a discriminating bias in itself. For instance, you should be diagnosing more females than males with breast cancer. So in data and algorithmic bias, what we refer to is systematic errors that are different for some groups than for others. Now, in order to detect this bias, this error, I need to be able to know what the truth is. But in diagnosis, this is often impossible. So our analysis depends entirely on being able to find a reliable proxy for the true label in order to even detect that there is a problem. An example of this is from a recent paper where a commercial algorithm was analyzed that used healthcare cost as a proxy for healthcare problems. Turned out this algorithm was hugely racist. It was developed in the US, where healthcare cost depends entirely on your health insurance coverage. And you could easily imagine some groups of society having poorer insurance coverage and therefore having fewer costs related to healthcare, even though they are just as ill as people with more costs. And in this paper, they discovered that if they exchanged this proxy for healthcare needs from healthcare costs, then the algorithms became less biased. So this is an example of how changing your proxy can make your algorithm less biased, and how your proxy is really important for what you get out in the end. When it comes to diagnosis, finding a proxy variable is very much an open question. What should we be looking at if we can't access the true diagnosis? Should we be looking at survival, perceived quality of life, or a continued need for treatment? Something else entirely? There's also a number of candidates for what a fair machine learning algorithm should be. One of the earliest suggestions was that your predicted outcome should be independent of sensitive variables such as gender or race. This is problematic in medicine, where your gender might actually influence the diagnostic criteria that should be used to diagnose you. So if you leave out gender, you might actually have less capability of getting a good diagnosis. This also becomes problematic with another notion of fairness called individual fairness, where people who are similar to you should have similar predictions. Because men and women who are similar in their measurements should maybe not have the same diagnosis. Another notion of fairness, called group fairness, asks that different groups should be treated equally. And this is what we saw in the first case, where we were lowering performance for the female group in order to have it with the same performance as the male group. But do we find it fair that one group should be diagnosed with less accuracy than what we can do just because we're unable to diagnose another? I don't think so. So this leaves us with an open problem, which is, what is fairness in healthcare? And very likely, this is going to need the involvement of more people than just technical people like myself. Thankfully, with me today, I have Sune, an expert in ethics, who will maybe help us a bit on that front.
To begin with, I think it's important to try to map out a little bit about what I will talk to or refer to as a algorithmic decision making and what it consists in. And this will help us perhaps identify why ethics is also relevant when discussing using algorithms in diagnostic contexts. So we might say that we have an algorithm that produces a prediction, say about whether someone who applies for a loan will pay back, or whether a person will develop cancer, or some other thing that we're interested in. And for the sake of the discussion here now and my presentation, I'll just assume that that prediction results in an automated decision. So if the prediction is that the person applying for the loan will not pay back, then the loan is denied, and so on. Now, in this sort of scenario, whether or not a person gets a loan actually has an impact on that person. Let's assume that it's beneficial to get a loan and harmful if you don't get a loan when you apply for one. Now, with respect to making the predictions, we are basically in a domain where we are trying to make a best guess about a feature of a person that we don't have direct access to. And that might be very interesting, and to try to develop tools for doing this as accurately as possible. So often a good algorithm is supposedly one that has high accuracy. Now that in itself might not be very interesting ethically. We can make algorithms that have high accuracy for predicting all sorts of things. Where ethics enters the discussion here is when the predictions that we're making are transferred into actions or decisions and actions that actually makes a difference to people's lives. And of course, for instance, in healthcare, if we want to use these systems for diagnostic purposes, whether or not you're diagnosed correctly makes a big difference to your life and your well-being. Finally, a thing I just want to note about the diagram here is also that it illustrates that there is both a consideration that we might take about the ethics of the process, that is, of using the algorithm to make these sorts of decisions, and we might have ethical discussions about how the algorithm is set up, how it's designed, say which predictive features are used, and so on and so forth. But there's also a question, which is the one that has been mainly focused on in the fairness discussion, which has to do with the distribution of the impact of using the algorithm. And I'll just quickly refer to an example which sort of kicked off a lot of the discussion about algorithmic fairness and ethics in algorithmic decision making. So in the US, probably some of you have heard about this case before, and there's use of an algorithm called Compass, and some investigative journalists, they looked at the performance of this algorithm in a county in Florida, and what they found out, allegedly at least found out, was that when the algorithm made mistakes about which defendants might go out and commit crime if they were released before their trial, when it made mistakes, it made the bad mistakes twice as often for black defendants and the good mistake twice as often for white defendants. So in the case you were black and you were in fact not going to reoffend, you had a much higher chance of getting a positive prediction that you would reoffend compared to whites, and vice versa. So in one of the comments, which I think sums up the problem about fairness here nicely, a commentator wrote that imagine a study that showed that in a particular court, innocent black defendants were convicted at twice the rate as innocent whites, while guilty whites were let off at twice the rate as guilty blacks. Now I think most of us would think that something about this seems unfair. And the problem of algorithmic fairness is that, in part, that very often algorithms will seem to have these consequences for different groups. So, just to clarify also a little bit, when we talk about discrimination by algorithms, as in the Compass case and perhaps also in cases in healthcare, we might think about discrimination in different ways. So sometimes people say, well, an algorithm can't discriminate because it doesn't have any negative attitudes towards anyone. It doesn't think, I mean, even if it's sometimes called artificial intelligence, it's not as if these programs actually have opinions about blacks and whites or women and men and so on, negative attitudes in general towards any specific group. They just do what they do. And of course, that's true, I guess. So in a way, they are not the sort of systems that will engage in what we will often call direct discrimination. That's the sort of discrimination you have when you, due to negative attitudes toward a particular group of people, treat them worse than you treat other people. But there's also this notion of indirect discrimination, which I think is the one that fits the case of algorithms here. So sometimes it turns out that a practice, a policy, or a decision process, as one using an algorithm, has very different impact on different groups of people. As we saw in the case with the Compass, it turned out that using Compass meant that black defendants suffered much more from the mistaken predictions about them than white defendants did, considered as a group. And that seems to be what generates the objections here. The discrimination consists in the fact that groups are treated very differently and that one of the groups is disadvantaged compared to the other. See, that's an ethical question we suddenly have to deal with here, because then we have to figure out, so what should we do about it? What's the right thing to do? And this is actually the core of ethics. It concerns what to do about these sorts of questions. Now, I think when we want to discuss the use of these algorithms in health-related contexts, say in diagnostic contexts, it's interesting just to consider a case that would be analogous to the Compass case, just with respect to, say, the development of a tool for diagnosing depression. So as Aasa just mentioned, we have some evidence, but this is something that some people will look more into, that diagnostic data is probably skewed such that women are over-diagnosed and men are under-diagnosed. So we could now, if we trained an algorithm to make diagnosis, depression diagnosis, we might get the following result when we tested it. The diagnostic algorithm turned out to be such that its diagnosis of non-depressed female patients was much higher with respect to false positives than with respect to men. So we could imagine, similarly to the case of Compass, that there was a study that showed that in a particular diagnostic algorithm that had been developed, non-depressed female patients were diagnosed with depression at twice the rate as non-depressed men, while depressed men were diagnosed as non-depressed at twice the rate as depressed women. Now, of course, this seems to show, if this study was true, then we had something that we had to consider, because then we would have to consider, is this a fair algorithm in the first place? And if it isn't, what should be done about it? How could we tweak the algorithm in some way that would make it fair towards these groups? And one of the things we would have to look at is which sort of impact here would be the worst one. Is it worse to be diagnosed with depression when you're not depressed, or not to be diagnosed with depression when you are depressed? Because that would be something that we needed to consider in order to assess which group was actually disadvantaged by this system in the first place. And secondly, of course, we would have to consider what to do about it. In the wake of the Compass debate, there were some solutions that were proposed or has been proposed in the literature on machine learning. So now we're coming back to the question about how to determine whether an algorithm discriminates against a group. So in the Compass case, there seems to be agreement that this was a case where discrimination seemed to occur against blacks. It's not so clear, perhaps, what would be the discrimination in the case illustrated with depression. Does the algorithm discriminate against women, or does it discriminate against men? And if so, why? But in the wake of this, there has been a few ways of trying to get around the problem of discrimination, or solve it, you might say. One suggestion has been to simply prevent the algorithm from using certain features. Now, this would be to try to avoid the discrimination in the design of the algorithm by simply disallowing that it had access to certain features about persons. The general argument against this view is that it doesn't really ensure that we avoid the differences that groups might experience with respect to outcomes of algorithmic decisions. So then a lot of people have suggested something else, or some other way of avoiding discrimination, namely to say that we need to get the right balance between different groups when it comes to, say, false positive rates and false negative rates. And many of these suggestions, one of them is called equal opportunity, that I have put on the slide in the bottom just to illustrate. Many of these, or pretty much all of these classification parity views, all trade in the idea that in order to achieve fairness in algorithms, we must achieve equality with respect to some important measure, say error rates or predictive values. Now, as an ethicist, this is an interesting claim, because what it suggests is that fairness in algorithmic contexts here consists in ensuring equality across groups with respect to some particular measure. But what it also seems to suggest is that it's equality with respect to probabilities of misclassification and not with respect to the harm that the groups actually experience. So one thing that it's important to look into here is how these different ideas of discrimination suggested in the machine learning literature might attach to these ethical considerations. Finally, I think that it's important also in this context to be aware that one of the important criticisms of Compass was that it traded, or the reason why it had these consequences for black and white defendants was that it was trained on data sets which had been produced through practices, say arrest practices in the US, which are biased against blacks, in the sense that they are criticizable for treating blacks harsher than whites when it comes to figuring out where crime takes place. And we might have similar issues arising in the context of the depression data, because one of the reasons why there might be bias in the data, if there are, has to do with the way the diagnostics has been approached. And there might be cultural stereotypes about women and men, which perhaps without doctors thinking about it, somehow guides at least partly the diagnostic practices and processes that we find in the data. And that might actually be reinforced if we train an algorithm on these data, and it then reproduces the very same patterns that have guided diagnosis of depression in the past.